Okay, Unit 4, Lesson 4.6, we're going to be talking about mutually exclusive events. So, mutually exclusive events are this. So, previously we talked about and. So, if we've got this symbol, we're looking right here, if we've got this symbol, it occurs in event A and B, both happen at the exact same time. Okay? Now, we've also learned that the or represents, the union represents or, meaning that A could happen, or B could happen, or both could happen. Now, we're going to consider a standard die. We're going to let A being an even number, and event B is going to be an odd number. Okay? So, we want to complete the diagram that we've got going on here. So, our diagram's down below. So we want to list the outcomes. So what are the even outcomes on a die? 2, 4, 6. What are the odd outcomes on a die? 1, 3, 5. Good. So that's what it wants us to list up here. Now remember, when we're listing, we are listing with our curly brackets. So 2, 4, and 6. And event B is 1, 3, and 5. So, what about A and B? Do we see anything with A and B? No, we don't, do we? What would A and B represent? What do we call that? It's a section that we call it a specific thing on a diagram. It starts with the letter O, and then a V. The overlap. So, and always refers to the overlap. Well, do we have an overlap situation? No, we don't. So that means this is going to be an empty set. Okay, it's an empty set. Now, if I wanted to list A or B, well, A or B means list all of A and all of B, which means all of the outcomes from the die. 1, 2, 3, 4, 5, and 6. Okay, that's A or B. This or includes all of A and all of B. Now, we want the probability of A happening. Okay, well, what is the probability of a 1, a 2, a 4, or a 6 coming up? How many numbers are there? 3. Out of how many total? Good. So we're going to get a 0.5 probability. So we get half a shot that we're going to get an even number. Well, what do you think B is going to represent? Is B going to differ from A? No, they're not going to be different because there's 3 even numbers and 3 odd numbers. So it's going to be exactly the same, 0.5. 3 out of 6 and 3 out of 6. Now, we notice that since the and was an overlap and we don't have one, it's an empty set, the value is 0. So we would represent empty set with a slash through our 0, whereas an and just means the probability of it is impossible. So this one, remember, if you put a 0 probability, it's impossible. All right, the probability of or. Well, how many numbers do I have in or? 6. Well, that's 6 out of my total, which is 1. Well, that means it's a certain event. It's a 100% chance. It's certain it's going to happen. Okay? Now, when we notice here that A and B had 0 elements, okay? It had absolutely no elements. And that's because we now have a new definition. They're called mutually exclusive events. So, mutually exclusive events do not have an overlap, okay? That means they do not have any common outcomes. Nothing about them is the same at all, okay? So, rolls an even number, rolls an odd number, okay? They are mutually exclusive events. They are also complementary events. Change that I there to an E, complementary, it's different. Right here, they are complementary events. Now, why would we say they're complementary events? Spelled wrong twice here, oh my goodness. So why would we call them complementary events? What is the complement of an event? How would we describe it in words? the opposite, or everything the other one is not. That's how we describe it. Because sometimes it's not always the opposite. In this case, even and odd are opposite. So in this case, it does work. But going to the opposite doesn't always work. So tend to do the definition of everything it is not. That's the complement. All right. So we know that the probability of A and B is 0 because it's mutually exclusive. These guys here do not overlap. The circles are separate. Okay? So if it's mutually exclusive, they're disjoint. Okay? So let's take a look here. So we've got ways that we calculate mutually exclusive and non-mutually exclusive. So we've learned how to separate things in the Venn diagrams, but we also have a probability formula. So the probability formula states this. For mutually exclusive events, they cannot occur at the same time. And what we're doing is we're comparing two events. We're not saying that they're happening right at the same time, okay? They can't. So what we're doing is we're only comparing and talking about one thing happening. In the next lesson, we're going to be talking about multiple things happening, but this is just one thing happening. So if I draw a card out of a deck, is it a diamond or a club? Well, diamonds and clubs have nothing to do with each other. That's why they're in separate circles here, okay? So they are mutually exclusive because I can't pull a diamond out at the same time I can pull a club out if I'm only pulling one card, okay? Remember, you're only pulling one card. Let's go now to non-mutually exclusive, the very opposite. So non-mutually exclusive means there's an overlap. So if I were to pull out again one card out of a deck, and I'm looking now for what am I looking for here? I'm looking for a king and a diamonds. Well, can I pull a king of diamonds out of a deck? Yes. So that means there's an overlap, okay, if they can occur at the same time. What it means by occurring at the same time means if specifically for cards, they're on the same card, okay? There is a king of hearts or king of diamonds. So occurring at the same time, that is the overlap we're talking about right here. All right, so let's do a couple examples here. We look at these. We want to see, are they talking about events that can happen at the same time or events that cannot happen at the same time? That's the difference. So let's look at the very first one. We're rolling a die. Can a number less than 4 and a number greater than 3, can that happen? Less than 4. So if it's less than 4, what numbers could it be? 1, 2, 4, 3. Well, then it says a number greater than 3. Is greater than 3 a number 1, 2, or 3? No. So these would be in completely separate circles, correct? Which means they don't happen at the same time. So that means we would say those are mutually exclusive because they're not happening at the same time. Okay? Let's look at the next one. You're going to draw cards from the deck again, and you're going to draw a face card, you're going to draw a club. Do those have anything in common? Yeah, there's 3 club face cards, Jack, Queen, King. So there's an overlap here. Wherever there's an overlap means it's non-mutually exclusive. Okay? It's non-mutually exclusive because they share elements. Okay, so B/C because they share outcomes. By sharing outcomes, I mean they have the same answers for outcomes, some of the same answers. So, meaning, are there face cards that are clubs? You bet there are. There's 3 of them. Example 3. 2 dice are rolled. Okay? I need both dice showing the same number, and then both dice have a value that add to 9. Well, can I have a double number on my die that's going to add to an odd answer? Let's take a look. Well, if I have a 1 and a 1, and I add them, I'm going to get 2. If I get a 2 and a 2, I'm going to get 4. A 3 and a 3 will give me a 6. So when I have double numbers on a die from 1 to 6, I'm always going to get an odd number for an answer. So is it possible to get them to add up to 9? No, they would not add up to 9. It's impossible. So that means this is mutually exclusive. There's no overlap, okay, because they can't add up to 9. They will always add up to an odd number, or sorry, an even number. Now we're going to look at the diagram with the circles. The diagram with the circles just to the right of that, we want to know which ones would be mutually exclusive. So in this diagram right here, which ones are mutually exclusive? So what I mean by that, which ones are not touching or overlapping? So which ones do not overlap? A with all of them. So A and B, A with C, A with D. They are mutually exclusive because they do not overlap. Which other two circles? There's one more. Good. B and D do not overlap and touch. Okay, so there's 4 events there, okay, that will not overlap and touch. So A, as we noticed, does not overlap and touch with any of the other circles. Okay, that's why it's mutually exclusive. So you could, another way to, if you're thinking of a diagram, mutually exclusive, it could be separate. Okay, they're not touching, they're separate. All right, let's take a look at our last couple examples here. So, we want to know when we're using our probability formulas. So, we want to know if they're mutually exclusive. So on our formula sheet, we're going to use 2 different formulas. One of them is this. The probability of A or B, and this other one, the probability of A or B. Now, the first one I'm going to show you is for mutually exclusive. The second one is non. I want you to let me know if you know why. Let's take a look at these equations. Probability of A plus probability of B. Probability of A plus probability of B minus probability of A and B. All right. What do you notice about those 2 equations? What is the difference between them? One of them I'm doing what at the end? I'm subtracting. This one is subtracting the overlap. It has to subtract the overlap, okay? Because the overlap in any Venn diagram has been added twice. That's why when we do our 2-circle and 3-circle Venn diagrams, we pull our totals out and then subtract from the totals, because each of them has to add it, and they've added it twice. So that's why we've always got to subtract the overlap in the end. Now that's if they're overlapping and non-mutually exclusive. Now right now, we don't know. So if we don't know, we always start with the very first one, this one right here. So we start with the first one, and we compare the information to what they give us. So if this is true, that means that the left side of the equation will equal the right side of the equation. So that means if I take the probability of this A, 1 over 4, and I add it to the probability of B, 1 over 3. If I add them together, they should give me that. That's what our first equation here tells me. I'm going to do the work just below here. So I'm going to say, well, A or B is 7 over 12. So 7 over 12 is the A or B. That's my left-hand side. Now, when I'm going to be adding or subtracting fractions, we need to deal with common denominators. So, since my or here, A or B, has a 12 on the bottom, I'm going to switch each of these into multiples that have a 12 on the bottom. So, then this one here, 1 over 4, becomes something over 12. What would it become over 12? If you're not sure, cross multiply and divide. What do you multiply by 4 to get 12? 3. So you're multiplying 1 by 3, which is 3. So this guy becomes 3 over 12. 1 over 3 becomes what over 12? 4 over 12. Good. So we're going to use those numbers, because if that top statement is true, my left side should equal my right side. So probability of A, 3 over 12. Probability of B, 4 over 12. If I add A and B, do they give me 7 over 12? Yes. So since the left side equals the right side, that means they are mutually exclusive. Okay? So number 3 is asking, are they mutually exclusive? We say, heck yeah, left side equals right side. Okay, and that's what we always have to check. Now, what if the left side did not equal the right side? What would that tell us? That there's an overlap, that we have an OR part, which is this, the overlap. Okay, so if the left side doesn't equal the right side, you've got an overlap that needs to be subtracted. And that's how often we have to find our AND equation, okay, which comes up further. Okay, I'm just going to erase all that information in a moment here. I'll let you get caught up and write that down. Okay, carrying on example 4. We're going to draw a card from a deck. Now remember, this one's only drawing one card, a card, so we're doing one event. We want the formulas to prove or determine that I get a 9 of diamonds or a heart. So I need to write down what my probability statement is telling me to do. So they're asking for a probability of a 9 or a heart. Okay? Well, that means we need the probability of a 9 plus the probability of a heart. Is there a 9 of hearts in the deck of cards? Do we have a 9 of hearts? Yes, we do. So, since we have a 9 of hearts, we're going to have to subtract it. So, subtract the probability of a 9 of hearts. Okay, so probability of a 9. How many 9s are in the deck? There's 4 of every card, so 4 out of 52. How many hearts are in the deck? 13. There's 13 of every suit, so 13 out of 52. Now, how many 9 of hearts are there in the deck? There's 1. So we're going to subtract 1 of 52. And that's going to give us our answer here, the OR, which is what we're looking for right here. So we add the top numbers. 4 and 13 give me 17. I subtract 1. That's going to give me 16 and 52, which we are going to reduce. Not sure. You guys have it? 413. 4 in 13 is what it reduces to. Okay? So, this one is a 9 or a heart. Okay, as we can see, Miss Tuck kind of read the question backwards. So look at what happened, guys. This one is B. I didn't do A yet. This one's B. Because A says a 9 of diamonds or a heart, and then B just says a 9 or a heart. Okay, so I have to do A after. So this is actually the answer for B, just so you know. So just put your answer for B on this one. So a 9 of or a heart, you have to subtract the 9 of hearts. But the next one, A, the very first one, said we want a 9 of diamonds. How many 9 of diamonds are in the deck? 9 of diamonds? That's one specific card. There's only one 9 of diamonds. So for number A, probability of a 9 of diamonds or a heart. Well, that's going to be probability of the 9 of diamonds plus the probability of a heart. Okay, so there's the work for that. Can I erase the work here for B? Almost. Okay, I'll just give you a minute to finish. Okay, back to let's finishing A now. If we take a look at A, if I want to do my probability here, I'm going to move this guy down where he belongs. So, my probability of a 9 of diamonds, there's 1 in 52. There's only one of that card. And how many hearts are in the deck we discussed? 13 and 52. So that's going to give me 14 and 52. And then we're going to reduce it. And we reduce to 7 and 26. Okay, so 7 and 26 is our answer. All right, let's take a look at number 5. Now yours, I think, still say, I don't know, I think they say pyramids and stars, but they should be triangles and stars. Yours might say pyramids and cylinders on your question. Just change it to triangles and stars. So, as you can see in my little yellow bag over there, we've got blocks of different shapes and colors. So some are cubes, some are triangles, and some are stars. We've got one blue cube, one red cube, one green cube. We've got one red and one yellow triangle. And then we've got a bunch of stars. 3 red, 1 blue, 1 yellow. We need to know a triangle or a cube. So let's write our proper probability statements. So we want probability of a triangle or a cube. Now you could have put T for triangle and C for cube. I just drew the objects, whichever you like is best. So probability of my triangle plus probability of my cube. Now, how many triangles do I have? 2 out of how many objects in my bag? How many objects are in the bag? 10, good. So 2 out of 10 are triangles. How many are cubes? Only 3 cubes? Yep, 3 cubes out of 10. We're going to add them all up. How many do we get for triangles and cubes? 5 out of 10, which is half. Okay? So half is a triangle or cube. Half of the objects. Now we're going to go over to B. A red shape is not picked. So what we want is this. Probability of red prime. That's what we're looking for. That means probability no red. Well, how many red objects do we have if we count them in the bag here? 5 red objects. So if we have 5 red, how many are non-red? 5. So that's going to give us 5 out of 10, which is half. Okay? We're going to go down to C here. C says a red shape or a star. Now this is where we get into overlaps again. We want red or a star. I want my bag to come down. Let's pull the bag down. Oh, is he locked? He's locked. That's okay. So we want probability of a red or a star. So we need probability of a red plus probability of a star. Do we have red stars? Good. So what do we have to do with our red stars? We minus the overlap. Red stars would be considered the overlap of both these ideas. Okay, so we have idea 1, which is red. Idea 2 is a star. Both those ideas, the overlap would be a red star. So we've got to subtract the red star at the end. Still got 10 minutes, guys. No packing up. So, now we're going to put in probability of red. Well, 5 out of 10 are red. How many are stars? 5 out of 10 are stars. How many are red stars? 3. So we have to subtract the 3 overlap, the 3 red stars. So we have 5 plus 5, subtract 3. So how many do we end up with? 7. Good. So the or is 7 out of 10. Okay? We got 2 last examples, and both of them can be solved with Venn diagrams. We have just enough time for them. Yep.
I don't know if it's just said a different order. It says or cylinders picked.
Right, I know, because I changed cylinders. This was cylinders, I changed them to stars.
Oh, okay.
So you have to change cylinder to star. Okay, sorry. Okay, last 2 examples. So we have a car manufacturer with a database, and they sell cars that have heated leather seats and some that have sunroofs. And some have neither. And we have some that have both. So it says determine the probability they're going to have both heated and a sunroof. So the first thing you have to do is fill in a Venn diagram. So we have heated leather seats and a sunroof. So 43 models have a heated leather seat. They sell 36 models, or 36% have sunroofs. 49% have neither. So 49 is our outlier. Now, if I'm talking percentages, we know that all 3 sections of my circles have to add up to 100% with my outlier. So 100% subtract my outlier gives me how much? What's 100% subtract my outlier? 51. So that means area 1, area 2, and area 3. Those three regions have to add up to 51. Okay? So this is where we take our total, and we're going to subtract 51. And that's going to give us our overlap in the middle. Now, what total am I talking about? I'm talking about the totals they gave us. They gave us 36 and they gave us 43. And if we add them together, there's too much, right? So we're going to add 43 and 36, and we're going to get 79. So they say 79, but we know it can only add to 51. That's why we have to subtract. That's how we get the overlap in the middle. So when we're going to subtract them, we're going to get a 28 overlap in the middle. Now we can subtract from 43 to find region 1, and that's going to give us 15. And then we can subtract from 36 to find region 2, which is 8. So the question's asking, are these events mutually exclusive? Why or why not? Yeah, we're saying no. I see a lot of head shaking. You're right. It's not mutually exclusive. So we're saying no. They are not. And the reason, because they have the overlap. Some have both. They share both. Okay? All right. Now we're going to take a look at our very last example. I'm going to let you guys do that one for homework. Push pause now and play when you're ready. All right, last example. We have 200 people with neurology symptoms that were included in a headache and backache study. So we're going to first solve it with a Venn diagram. So if I use my Venn diagram here, I have two things going on. We've got headache and backache. So we're going to put the totals for each. So for headache is 60, for backache is 126. So now we are going to take a look, and it says 36 experience relief from both. So that one is our overlap. So we're going to throw that number in first. Now we're going to subtract from 60 to get the other two numbers. There's our 24. We're going to subtract from 126 to get 90. Now if we take a look, it says all the people received some relief. So that means there's no outlier. All right, so the question wanted to know, what is the probability of a person having relief from at least one of the two symptoms? Well, that means one or both. So that means we would add up everything in our diagram. So adding up everything in our diagram is going to give us 150. So for A, we would have 150 over 200. Okay? That's going to give us a probability of 0.75. So 75% of the people had relief from both. Okay? I was incorrect when I said there's no outlier. Only 150 people, and they surveyed 200. That means 50 is the outlier. Pardon me there. Okay, so now we're talking about doing the exact same thing with the probability formula. So if I want probability of headache and backache being relief, headache or backache. So at least one, so it must be headache or backache. So that's probability of a headache plus probability of a backache minus the overlap. So we're just going to move this down a little bit, make it a bit smaller. And then we're going to subtract probability of the overlap, headache and backache. Okay, so we don't know the order, that's what we're looking for. Probability of a headache is 60 out of 200. So 60 out of 200 experience relief. Those are our big totals here. Backache is 126 out of 200, which is our total here. Then we have 36 that experienced both. We always have to take and subtract our outlier. So we've got 36 over 200. This is going to give us a total of 150 over 200, which is equal to our 0.75, which is what we got over there with our Venn diagram. So 75% of the people receive. Okay, so now we need to do neither of the symptoms. So neither of the symptoms, well, if you're not gonna have one of the symptoms, we're gonna have the complement to this. So we need to have the 0.75 plus something gives us one whole. Well, neither of the symptoms, we have 50 people as our outlier. So we would have 50 out of 200, which would give us 0.25. So over here, probability formula, if I insert our 0.25, our event and our complement are going to add up to 1.0 as we know. Check your work, make sure that yours matches mine. This is the end of 4.6.